So hi everyone, this is Dr.G.Ravindranath Reddy, working as Assistant Professor of Mathematics in MLR Institute of Technology, Hyderabad. In this video, we are going to discuss the Fourier series expansion for the discontinuous function in the interval 0, 2 pi and minus pi, pi. So now, first we will take one example how to find out the Fourier series expansion for the discontinuous function in the interval 0, 2 pi. So this is the function he has given, f of x is equal to 1. This f of x is equal to 1 whenever that x lies between 0 to pi, and we can take f of x is equal to 0 whenever that pi x lies between pi and 2 pi. Now here in the first condition the initial value is 0 and in the second condition the final value is 2 pi. So we can consider from this, we can consider this is the interval 0, 2 pi. Now in this interval we are having two conditions, one is x lies between 0 to pi and the next one is x lies between pi to 2 pi. Now in this, by using these conditions we got the interval 0, 2 pi. Now in this interval for this function we are going to find out the Fourier series expansion here. So now the standard formula of Fourier series expansion for the discontinuous function is similar to the function for which we are going to find out the Fourier series in the interval 0, 2 pi. So that is given by f of x is equal to a0 by 2 plus summation n is equal to 1 to infinity an cos nx plus bn sin nx. Now similarly, this is the formulas to find out the a0, an and bn values here. So this we can call it as a Euler's coefficients. Now which is similar to the values of a0, an and bn which we have discussed in the interval 0, 2 pi. Now let us go for the a0 value. So that a0 is given by, since the interval is 0, 2 pi, so a0 is equal to 1 by pi integral 0 to 2 pi f of x dx. In the previous videos we have seen we got only one function, one value of f of x, so we have substituted directly that f of x in place of f of x in this interval. But here this is a discontinuous function, so based on the conditions we got the values of f of x. So according to that conditions we have to divide this interval 0, 2 pi into two subintervals. One is 0, 2 pi and the next one is pi to 2 pi. Now divide this, integral 0 to 2 pi can be written as integral 0 to pi and integral pi to 2 pi. Now in this substitute the values of f of x here. So in the given function he has given f of x is equal to 1 whenever that x lies between 0 to pi. So in this integral, first integral I have taken that f of x is equal to 1, and whenever the x lies between pi to 2 pi he has given that f of x is equal to 0. So I have taken that f of x is equal to 0 in the second integral. Now integral of 0, that is 0. So this integral we can neglect this integral and you concentrate only on the first integral whose limits are 0 to pi. So integral of 1 dx, that can be written as x. So 1 by pi into x, substitute the limits 0 to pi, then we can get our required value, that is a0 is equal to 1 here. Next go for the an. So an value he has given as an is equal to 1 by pi integral 0 to 2 pi f of x into cos nx. This is the standard formula to find out the an value in the interval 0, 2 pi. Now here also we have to divide this interval 0, 2 pi into two subintervals, that is 0 to pi and pi to 2 pi. So we have divided this integral 0 to pi and pi to 2 pi. Similarly here also you substitute the value of f of x based on these conditions here. So in this 0 to 2 pi the f of x value he has given as 1 and pi to 2 pi that f of x value he has given as 0. So integral 0 into anything equal to 0, integral of 0 is 0, so we can neglect this second integral. Now concentrate only on the first integral whose limits are 0 to pi. So now the remaining one is 1 by pi integral 0 to pi cos nx dx. Now we have the standard formula to find out the integral of cos. Take that value, integral of cos nx is given by sin nx by n, and substitute the limits 0 to pi. Substitute the upper limit here. So you take this denominator outside since it is a constant. So 1 by n pi. So replace x with upper limit. So sin n pi minus sin 0 lower limit. So sin n pi is 0, already sin 0 is 0. So 0 minus 0, 0, 0 into anything equal to 0. So you will get that an value is equal to 0. Now we got a naught is equal to 1 and we got an is equal to 0. Now we have to go for the bn value here. So to find out the bn value, he has given f of this bn is equal to 1 by pi integral 0 to 2 pi f of x sin nx dx. So like in the previous, here also you divide that integral limit 0 to 2 pi into two subintervals, integral 0 to pi and pi to 2 pi. And then according to the condition, substitute the values of f of x in these two integrals. So as usual, whenever this x is lies between 0 to pi, so we got that f of x is equal to 1, substitute that f of x is equal to 1. And whenever that x lies between pi to 2 pi, he has given f of x is equal to 0. So 0 into anything equal to 0, integral of 0 is 0. So we can neglect this second integral. Now concentrate on this first integral. The remaining one is 1 by pi integral 0 to pi sin nx dx. So integral of sin nx dx he has given as minus cos nx by n. Now in this substitute the upper limit and lower limit here. So you will get minus, you take this minus outside. So minus 1 by n pi cos n pi minus cos 0. So we know that cos n pi is equal to minus 1 whole to the power of n and cos 0 is equal to 1. So here, so already we said that whenever we are having the terms minus 1 whole to the power of n and constant term 1, then we can go for the n even values and odd values of n here. So whenever we take n is equal to even value, so n is equal to even you take, that is n is equal to 2, 4, 6 like this. If you take n is equal to an even value, minus 1 whole to the power of 2, that is minus 1 whole square, you will get 1. So 1 minus 1, 0. So whenever we take n value as even value, we are getting that bn is equal to 0. For n is an even value, we are getting that even. For n is equal to even, we are getting bn is equal to 0. And suppose if you take n is equal to odd here, so odd is n is equal to 1, 3, 5, 7. So if you take n is equal to 1 here, minus 1 whole to the power of 1, you will get minus 1, minus of minus plus 1, 1 plus 1, 2, 2 by n pi. This is the value when we can take n as odd number here. Okay. Now whenever we take n as even number, we got bn is equal to 0. Whenever we take n as an odd number, we got bn is equal to 2 by n pi. Now we got a naught value and an value and bn value. You substitute these three values in the standard Fourier series expansion, that is given by equation 1. So now substitute a naught, an and bn in equation 1, we get our required Fourier series here. So here a naught is equal to we got that value is equal to 1. So a naught by 2, that can be written as 1 by 2, and since an is equal to 0, we can neglect that second term which contains cos nx. Now you substitute that, you substitute this bn value. So bn value we got this bn value whenever we take n as odd number. So we can neglect the even values of n in the summation. So that's why I have taken only odd values of n here. N is equal to 1, 3, 5 up to infinity. So now we got that value is equal to 2 by n pi, that is bn value when we take n is equal to odd value and sin nx. So this is our required Fourier series expansion. So in the interval 0, 2 pi for that discontinuous function. So whenever we apply this summation here, so we will take n is equal to 1 here. So from this 2 is constant, so I have taken 2, and the denominator pi is constant, so I have taken pi outside. So the constant term is 2 by pi. You take this 2 by pi outside this summation, and for the remaining value you apply this summation by taking n is equal to 1, n equal to 3, n equal to 5. We will get sin nx by n, the remaining one. And if you take n is equal to 1, you will get sin x by 1, that can be written as sin x, plus sin 3x by 3 plus sin 5x by 5, and so on. So this is our required Fourier series expansion in the interval 0 comma 2 pi for the function which is discontinuous. Now we will take one more example how to find out the Fourier series for the discontinuous function in the interval minus pi comma pi. So let us take this problem and we will see how to find out this Fourier series in the interval minus pi comma pi. So this is the function he has given, that f of x is equal to, he has defined as f of x is equal to 0 in the interval minus pi comma 0, and that f of x is equal to defined as pi x by 4 whenever that x lies between 0 to pi. For this function we are going to find out the Fourier series in the interval minus pi comma pi. Now you take the standard formulas to find out the Fourier series which we have discussed in the interval minus pi comma pi. As usual, you take all the formulas as it is. So that f of x is equal to, this is the standard formula to find out the Fourier series in the interval minus pi comma pi, and this is a naught value. This is the standard formula to find out a naught, an and bn values here. Now one by one we will find out that a naught, an and bn. Then we will substitute that these three coefficients in the equation 1. Then we can get our required Fourier series for this function in the interval minus pi comma pi. So now a naught is equal to, this is the standard formula. Now here also in the given problem f of x is defined. We are having two values for f of x. One value is equal to 0 in the interval minus pi comma 0, and f of x, he has another value of f of x he has given as pi x by 4 in the interval 0 comma pi. Based on these conditions we are going to divide this interval minus pi comma pi as minus pi comma 0 and 0 comma pi. So according to that we will take that integral minus pi comma pi as minus pi to 0 and integral 0 to pi f of x and here f of x. Now by satisfying these two conditions, just replace the values of f of x here. So whenever our x value lies between minus pi to 0, he has given that f of x is equal to 0, and whenever we are having the interval whenever the x lies between 0 to pi, f of x, he has given that f of x value as given by pi x by 4. Now since inside the integration we are having 0, so this integral value becomes 0, so we can neglect this and you concentrate only on the second integral whose limits are 0 to pi. So here 1 by pi, pi is constant and the denominator 4 is constant, so take pi by 4. The remaining one is x, integral of x dx, that can be written as x squared by 4. Now substitute the limits, upper limit and lower limit here. You will get this value is equal to pi square by 8. So that is the value of a naught here. Now similarly take next coefficient, that is an, which is given by 1 by pi integral minus pi to pi f of x into cos nx dx. Similarly you divide this integral limits minus pi to pi into two subintervals. One is minus pi to 0 and the next one is 0 to pi. In those two intervals you substitute the values of f of x here, that f of x is equal to 0, and that in the second condition the f of x is defined by pi x by 4. Okay. So as usual, since inside the integration we are having 0, 0 into anything equal to 0, integral of 0 is 0, so we can neglect this first integral. Now you concentrate only on the second integral whose limits are 0 to pi. So here you take pi outside and the denominator 4 outside. So the remaining one is x into cos nx. As usual, whenever we are having a product of two functions inside the integration, we have to go for the integral of uv formula. Now integral, apply the integral of uv. So you will get u into integral of v, that is cos nx. Integral of cos nx can be taken as sin nx by n minus, take the derivative of this u. U is x, derivative of x is 1, and this u we can consider as v1. Now then go for the integral of v1, you will get minus cos nx by n square. So After applying this integral of u integration by parts, we got this integral value. Now simplify this here, x into sin nx by x minus into minus plus cos nx by n square. Substitute the upper limit and lower limit here. So finally you will get this value is equal to 1 by 4 n square minus 1 whole to the power of n minus 1. So here also inside the brackets we are having minus 1 whole to the power of n and the constant value 1. So here you take even values and odd values of n. So you will get these values of an. So whenever we take an is equal to odd value, you will get this value is equal to minus 1 by 2n square. When we take n is equal to even value here, minus 1 whole square, that you will get 1, 1 minus 1, 0, 0 into anything equal to 0. So for this an also you will get two values. One value is when n is odd, you will get this an is equal to minus 1 by 2n square. If you consider n is an even number, then you can take an is equal to 0. So this is the value of an. Now go for the bn. Apply the same procedure here. Divide this interval minus pi to pi into two subintervals. In both cases substitute the values of f of x. So here same 0, 0 into anything equal to 0. Integral of 0 is 0. So we can neglect this first integral. Now concentrate on the second integral. You will get this, and take in this you take numerator pi and the denominator 4 outside. So you will get this one. For this also you apply the integral, because x into sin x, the product of two functions. Apply integral of uv. You will get this u into integral of v, that is sin nx. Integral of sin nx by, we got this minus cos nx by n, and minus derivative of x is 1, and integral of this minus cos nx by n, we can take this value. So by simplifying this we got this. Now you substitute the value of x, upper limit and lower limit here. So if you substitute the upper limit and lower limit here, you will get 1 by 4 minus pi cos n pi by n. So this cos n pi, we can replace that cos n pi with minus 1 whole to the power of n by 4n. So this is the value of bn. Now we got a naught, an and bn values. Now it's time to substitute all these coefficients in equation 1. So you will get that value is equal to a naught, an and bn value in equation 1. So you will get our required Fourier series expansion here. So if you simplify this, you will get this. So in this video we have discussed how to find out the Fourier series expansion for the discontinuous functions in the interval 0, 2 pi and minus pi, pi. In the next video we will see how to find out the Fourier series expansion of f of x in the arbitrary intervals. Up to now we have seen the intervals only in terms of pi, that is 0, 2 pi, that is one interval, and minus pi, pi, that is one interval, and we have taken the interval 0, pi. So these are the predefined intervals. In these predefined intervals we have seen how to find out the Fourier series for f of x. In the next video, instead of taking this pi, these intervals, we will take some constant intervals, that is like 0, 2, or once minus 1, 1. Like this we will take some intervals that we can call it as a arbitrary intervals. For that arbitrary intervals, in that arbitrary intervals we will see how to find out the Fourier series of f of x. Thank you.